electrical and computer science at the University of Missouri. He did his Ph.D. at the University of Tennessee in Knoxville. His research interests are varied in terms of all the different kinds of applications that he's worked on, but the focus is on the design, simulation, and experimental validation of inkjet-printed nanoparticle-based flexible sensors and electronics. It allows you to do in-situ computing with low-power analog and radio frequency integrated circuits and systems, short-range wireless telemetry, energy-efficient neuromorphic circuits and sensor systems, machine learning for sensors and systems, analog, orthogonal pulse-based, spectral efficient, high-density wireless telemetry. Lots of flexibility in here. And as I've worked on this project with Dr. Haider, I've seen just what wonderful capabilities he has, which I think has the potential for being applied to a variety of different projects in this space. So with that in mind, I would like to turn it over to Dr. Haider.
Thank you, Dr. Skubics, for such a nice introduction. And welcome, everyone. And this is my pleasure to be here and to talk about my today's topic. So if I may share my slide.
And as we have Dr. Haider talk, please put your questions in the chat box, and we will look at those at the end of the talk.
Thank you again. First, just I want to make sure that all of you can see my slides.
It looks good, yes.
Okay, thank you. So once again, this is my pleasure to present this topic. And today I will specially highlight one of that fabrication scheme for design and development of our sensors, devices, especially targeted for healthcare monitoring. So a most traditional one is our silicon-based technology that what we have been seeing for many years. But now there is also a time to pivot from that point and then how to go for some other affordable, largely deployable scheme. And that's what I'm trying to highlight a little bit over here. So the title of my presentation is, as you can see, it says minimally processed inkjet-printed flexible sensors and electronics. And obviously, we are trying to frame it for a low-cost alternative for silicon fabrication. So in my presentation, I will highlight what's the motivation behind this sort of design alternative or fabrication alternative. And from that point, I'll give a brief history of our well-known silicon-based electronics. Then my topic will move to this printable flexible electronics. And under that category, I'll try to highlight the inkjet-printed sensors and some of the applications that we have been doing. My next part should be inkjet-printed nonlinear devices or some sort of active element. And finally, how to utilize those active elements or nonlinear devices to frame or to form some sort of machine learning architecture. And finally, I will have the conclusion. So the highlight of this topic is obviously how to create a hardware platform outside of the clean room facility. So as you can see, we are living in a sea of sensors. So all of the places that we are observing, somehow we are being monitored or our data is being captured, collected, and there is a tremendous applications for healthcare devices, industrial automation, agricultural safety, and so on and so forth. So whenever we are talking about all of these things, we are basically moving to some sort of like a connected network, connected devices, especially for these days, internet facility, wireless communication, nano and microfabrication technologies. This has become a much more easier and simpler. So the trend is how to connect all these devices under a single network and create some sort of like a connected community. And whenever we look at that structure, it's not coming free. Obviously, it is also bringing some challenges, like say the number of devices, the number of units are growing rapidly. We are thinking of billions of devices coming to the network. Unlike our standard computer or cell phone based network, now we are talking about each and every device should provide data to the network, and how this could be solved, how could be done. And the market study is showing that the growth rate is even faster, the growth volume is even higher, and that is even higher than the pre-COVID era. So to tackle those challenges and at the same time to keep the device module in an affordable way, meaning that low cost, widely deployable, and easy for integration, considering all of these things, there is also a definite need for some other new kinds of fabrications or device development and processing scheme. So before going to that topic, I will try to highlight a little bit of our traditional or the ongoing semiconductor fabrication schemes, how it started, how it has evolved, and what we are at the present stage. And then I will move to our printing technology portion. So if you look back, the first transistor was formed in 1947 at Bell Labs, and then by William Shockley, John Bardeen, and Walter Brattain. So they got the Nobel Prize in 1956, and that was the start of our semiconductor scheme. Then first single transistor-based integrated circuit was formed in 1958. Later on in 1963, we saw the formation of our complementary metal oxide semiconductor-based logic gates. Then slowly, first microprocessor was developed in 1970. And if you can look at these things, at that phase, it was only 2,300 transistors and 740 kilohertz clock frequency. And even at that time, it was like an amazing scheme, how these integrated circuits can do so much work. Then we moved to a new era. It's called the very large scale integration, and that was in 1978. And the number of devices were like more than 20,000. And beyond that point, the number of devices has increased much more. So in the research community, there is a new term called the ultra large scale integration, but I think that naming didn't accepted, or it didn't appreciate it that much. So we, in the research community, we are still very much accustomed with the very large scale integration. So by saying very large scale integration or VLSI, we are actually talking about even like a trillions of devices in these days. So now, who is really driving this sort of like integration? Who is really driving this sort of like a density in our integration level? So the most obvious one is the functionality. How much or how many functions we can really integrate in our units or chips. So once again, if I look at these things, so when the first single transistor system was developed or the processor developed, it was only having like only one transistor-based gate in 1958. Then slowly in 1960, the first logic gate or first chip was having only one gate. And gate is simply a combination of transistors that can do some sort of like a logic function. It could be NAND gate, NOR gate, all those things. In 1962, the gate numbers increased to 2 to 22, 20, 64. We can see slowly are moving to some sort of complex functions with 20 to 100. Then we started with this medium scale integration, having 100 to 1,000 gates. Then it comes the large scale integration in 1972. Slowly, we are seeing the number of gates to the level of thousands, 1,000 to 20,000. And VLSI, it was like beyond 20,000 gates. And in the late 90s, we also started seeing the integration of multiple IPs or multiple chips in under one modules, and that's how it framed the term called system on chip. Later on, we also saw the system in package, heterogeneous integration over there. So if you really look back and try to investigate the driving force over here, so obviously these complex function, the need for complex function for our data processing, for our telecommunication need, all these things are simply driving these higher density, larger number of transistors in our systems. And this is also supported by the rapid progress of our processing technology, micro and nano fabrication schemes. So how can you really fabricate nanoscale devices and all these different units? And the most recent one, as you might have seen, the Cerebrus wafer scale engine 3, the third generation one. It has, so this is the AI engine, but wafer level integration. It has like almost 4 trillion transistors, 900,000 AI optimized cores, and 44 gigabytes of on-chip SRAM. So it's a massive unit. So, and the revolution was successful because of their new types of signal routing, utilization of the full wave for this large system development. So when we're talking about this sort of development and semiconductor industry, the growth, all these things, so it is basically targeting the feature size, the how we are actually shrinking our device. And if you look these charts, so the early phase, the first transistor was formed at the length of the human hair, only 80 microns. So that is the human hair length. And our first transistors are actually formed like around that dimension. Then slowly we started reducing the channel length or the feature size. By 1997, we see like a 0.25 micron devices. By mid 2000 or around 2000, close to 2010, we started seeing the 130 nanometer process, 180 nanometer process. And I myself used 130 nanometer process, 90 nanometer process for my chips fabrications, device development, all these things. This trend is not stopped over here. It is still growing. And the trend is like, okay, slowly the device feature size will become much smaller, even less than 10 nanometer, close to 1 nanometer. And over there, we are talking about some sort of like a quantum effects, quantum devices. So those things are actually coming. And over here, there is a well-known phenomena or well-known laws is called the Moore's doubling effect. Moore's law proposed by Gordon Moore in 1960s. So there is a point like when we thought about that maybe this law will not longer be valid because of the fabrication challenges, but still we see that sort of trend going on. And in the market-wise, definitely semiconductor industry is one of the biggest market in the world. So in 1924, the sales were like around like a 626 billion dollars. And in 2025, it was expected around like $697 billion. So obviously, this is the most tremendously growing market in the world. And obviously, it is actually revolutionizing all of our units, lifestyle, how we form our systems, development, all these different things. So now if you look at these things, then why and how this silicon-based technology is getting like that much popular? Why that is like still dominating the world? So obviously one of the part is called the abundance of the material. The silicon that we can get is very easy to reach. So it's coming from the sand and the processing is much simpler and the manufacturing facility is much more mature, all these things. But then we also having some sort of concern that how long this process is going to be continued, like how far we can really go. At that same time, also a burning issue is coming. How can you really make it much more affordable, widely deployable, something like that? So that triggers some other design alternatives like inkjet printing technology. So how can you really process or form our device even at room temperature? Instead of going to some clean room facility, can you really fabricate or really cook our device, our systems, our circuit boards at room temperature system? Can you form something other than the transistors, like memory structured devices? which will also have some other innovative features. Can use some exotic particles, nanoparticles. And one of the common example is the carbon nanotube-based transistors. So all these things are actually some new trends, new directions that people, researchers are actually exploring. So in today's presentation, I will mainly highlight this inkjet printing and how this can provide us a design alternative for low-cost, affordable scheme for a next generation affordable device and fabrication scheme. So what is inkjet printing? So simply, so inkjet printing works based on simply dropping some material on a certain substrate, and that is like a drop on demand based system. So it's another version of like additive manufacturing. We can also frame it like this way. So the idea is that all this inkjet printing portion is simply based on some like a nozzle. Instead of like a etching and cutting in standards silicon fabrication, we try to put the material on top of a certain substrate based on our demand or based on our need or based on our pattern. And over there, usually like two types of nozzles are used. One is the piezoelectric and another one the thermal. In piezoelectric version, the chamber is compressed or expand based on this electric potential. And because of that movement of this diaphragm in the piezoelectric plate, the right amount of ink droplet comes out, and that's what we can see the substrate level. Whereas in the thermal version, there is a resistive heating element. So that heats up the ink, creates a bubble, and that's how it creates the droplet. So considering these two types of inkjet printing process, so in our standard office printer, most of the time we see the thermal or the piezo, that both versions are available. But when we're talking about printing nanoparticles or custom materials, then in that case, piezo printing process, a piezo nozzle can definitely provide a upper end because of no temperature is involved over there, and so no flammability issue is actually creates a concern over there. And as you can see, when we're talking about this printing portion, so we can actually utilize almost entire amount of like a material. So that's why the efficiency, the printing efficiency or material efficiency is almost 100%. And whenever we have that much efficiency, unlike silicon one, so then that also gives us the opportunity or flexibility to use even some other exotic nanoparticles. Those nanoparticles that we can see, maybe they are expensive in some level, but whenever our utilization is that much highly efficient, then definitely that reduces our overall pricing or the cost from our final fabrication. And another benefit is inkjet printing is that we can fabricate our devices on any kind of substrate, thin, flexible substrate, and that could be paper, plastic, polymer, even rigid surface. So it's a combination of flexible and rigid. Both surfaces could be treated through this inkjet printing process. And that's obviously another beautiful features over here. So now, if you really do a side-by-side study, comparative study between this inkjet printing and silicon-based technology, so what you can really see. So the first one is the substrate level flexibility. So obviously, when we're talking the inkjet printing, it is compatible with flexible, stretchable substrate, even in the textile or the fabric level fabrication that is possible through the inkjet printing process. Whereas for the silicon-based one, it is limited to the rigid and brittle and sometimes the mostly planar surface. So that's what we can do. Fabrication cost, obviously inkjet printing is much cheaper than the silicon one because the inkjet printing process doesn't involve any sort of like a clean room setup, any sort of like a control environment or high temperature processing. Nothing is involved over there. So whereas for the silicon one, definitely we need to maintain a highly expensive clean room environment, and that makes the fabrication cost and also the affordability much higher. Processing temperature, room inkjet printing process could be done less than 150 degrees Celsius, whereas for the silicon one, we need almost like 1,000 degrees Celsius. So definitely much higher. And that's because of that, we cannot really afford to have like a plastic type of film or flexible substrate through the silicon fabrication process. Customization and rapid prototyping, definitely inkjet printing can provide a better higher end. It's simply defined as like a digital design to device compatibility, meaning that whatever the pattern we can design in our software end, we can directly print that device structure to our substrate. Whereas for the silicon version, we have to go through different steps: photolithography, mask formation, etching, cleaning, and repetitive process. And that makes it much more long-term, long time duration for a fabrication unit. Scalability, obviously, inkjet printing is ideal for large-scale, disposable, or low-power sensor systems. That's a critical need for our large-scale sensor device formation. And the silicon doesn't provide like that sort of benefit. So definitely this is a cost prohibitive for wide area sensor. So we can get high precision, high resolution, but whenever I'm talking about this massive amount of sensor device formation, then definitely silicon is not the best technology. Integration part, obvious, again, inkjet printing can show us, give us a better opportunity. So it can be biocompatible inks, and also like a printing on a biocompatible substrate, and interface because of the flexibility of the substrate. Sometimes this printed device, printed units could be easily fit to like a non-conformal surface. Silicon one, because of their rigidity and lack of biocompatibility, definitely that could be a critical part for integration. Flexible sensing electronics market. So we always say this, or we are defining this flexible electronics market is in its infancy right now, but we see a rapid growth pattern over there. So in 2024, the sales was like almost like a 36 billion. 2025, the projection is almost like a 41 billion, and with a compound annual growth rate of 14%, we are expecting around $70 billion dollar market at the end of 2030. And in terms of device formations, sensor formations, we see so many different types of devices, units, modules, passive and active elements are coming to the market. There are several small companies also being formed, and we see a booming area over here. And hopefully, we'll see the real benefits in the coming years. So over here, I'll slowly highlight some of the printed sensors, devices, units that actually we are forming, we're working. And hopefully that will also highlight the different potentials with minimal processing at scheme. So in my lab, we are doing the design, modeling, and fabrication of these low-cost, scalable, flexible electronics units, devices. We are highly utilizing our inkjet printing facility, which for like additive, maskless, and on-demand fabrication process. Definitely, it is targeted for wearable, disposable, and smart electronics. And our research and investing also goes to like a predictive modeling of ink substrate interactions, drying dynamics, and electrical behavior of printed units. So the process is a very straightforward over here. So it starts with like a design and modeling. So in our lab, we use KiCad, EasyPC, or any other like a PCB design software, or any other drawing software could be utilized over there. For modeling purpose, we have MATLAB, Python, PyTorch, that sort of module. Then for finite element simulation, we rely on the Sonnet or COMSOL multiphysics, that sort of model. So once we have the design is ready, or design pattern is ready, so simply we take it to our printer. We have three different types of printers. Like one is the Diametics material printer, Volterra one, direct ink printer, or even like a standard office printer. And for that purpose, standard office printer, we have retrofitted these things with nanoparticle inks, and that's how this low-cost platform can also create a nice-looking printed device and units. So ink selection-wise, it depends upon our application. So what sort of ink and what sort of properties that actually we are looking for. Once the inks are printed to our desired substrate, we simply go with like a curing process or annealing process, and our device is ready. So it is like that sort of like a simpler approach over there. Once the unit or device is fabricated, we simply go with like a contact formation, either with soldering or epoxy formation, and then sometimes some of the cases we provide the shielding or insulation, and finally it goes to characterization with our either through the optical microscopy or source meter, and we also target for the machine learning based characterization and the application. So as you can see, there is a commercial version of the nanoparticle printer, which is coming from the Fujifilm. Otherwise, we also configured a standard office printer in our lab, and that can create or print both conductive, semi-conductive, dielectric inks. Substrate-wise, we can use paper, PET film, PDMS sheet, FR4, cellulose. For our ink selection process, it goes to silver, graphene, hexagonal boron nitride, carbon nanotube, organic polymer, and even recent days, we are also using the graphene quantum dot ink. And that shows us different types of sensing parameters like temperature, humidity, vibration, pH, and so many other gas elements. So over here, I'm trying to highlight some of our fabricated and also reported work. The first one is the inkjet-printed graphene sensor, and that was targeted for the respiration monitoring. So idea is that these breathing patterns sometimes create some critical biomarkers, either for sleep apnea or pneumonia or so many other things, like how the breathing portion can create a like early stage biomarker to measure that breathing pattern. So our first sensor was formed based on this silver nanoparticle ink. We have this silver-based interdigited pattern, and right on top of this pattern, we had a thin overlay of like a graphene layer. So whenever we have this sort of architecture, this was because of this graphene, it was getting this temperature sensitive, and it was simply measuring the breathing temperature from the human airflow, the mouth breathing portion. We customized a medical grade spirometer by inserting our printed sensing unit over there and connected with a source meter to see the change, different volumetric breathing profile and the corresponding resistance change. And as you can see with the different volume pattern, we can see different response, different level of resistivity. And another critical one was that, okay, it was actually consistently highlighting the breathing cycles. So like how well the breathing portion is happening. We also tested with some like abnormal breathing portions. It's a mix up of like low volume, high volume. We also tested with occasional stop breathing and how well our sensor was actually capturing those events. In our laboratory-based test and validation phase, it was actually capturing that portion very nicely. So target over here is always a short time breathing screening process, like in a remote areas or in a home environment. If you really want to measure those breathing pattern, and then by having these electrical signals connected with transmitters or other units, we can actually easily even transmit the signal to a remote locations. So this sensor is actually capturing the first level electrical signature or digital signature from our breathing portion, and that can actually take us to the next level, system level integration, and even the network formation. So our next breathing portion was like a little improvement of our previous one. So over here we use the silver and hexagonal boron nitride. So again, we have this interdigited pattern, but then on top of this interdigited pattern, instead of graphene, we use the hexagonal boron nitride ink. So hexagonal boron nitride is kind of an insulating material, high bandgap, soft insulating material, and because of that material properties, it was actually showing like a higher amount of charge density. And based on our measurement, we have seen almost like a 30 to 40% increase in charge density, and that resulted a higher level of electrical signals. We also simulated our architecture through the COMSOL environment, and that was actually highlighting that how the electric field strength was actually increasing because of this inclusion of the hexagonal boron nitride ink. So we inserted that sensor in a face mask, and my student was volunteered to like simply do a breathing test over there. Once again, for a short-term breathing test, it was nicely capturing all these breathing profile, and then that digital signature was actually coming precisely in our unit. Our next investigation was like forming a foot sole sensor to monitor different like walking patterns. So over there we have this interdigited, no, instead of interdigited one, we have like this cross sign. So we had this silver-based cross sign, and then at the middle we have this hexagonal boron nitride ink during the gap area, and then we also introduce a physical cut. So that physical cut was introducing another nice challenge. So it's not only increasing the charge, but it is also creating an interfacial layer. And because of this interfacial layer, there is like a charge trapping effect. And whenever we had this charge trapping effect, that was making our sensor much more sensitive to vibration. And that's the vibration that actually we capture through our different activities like sitting, standing, walking, jogging, those sort of things. Based on these electrical signals, we investigated those patterns or behavior through different machine learning algorithms. And based on our study, we have seen that kernel SVM was showing the better classification. And our confusion metrics was also highlighting that performance, that how it is actually capturing different events, even from this minimally processed sensor portion. And ideas over there, like whenever you're combining these sensor behavior with the embedded machine learning feature, my classification, my signal acquisition or signal characterization becomes much more applicable to real life case. So our next portion was like an Inkjet-Printed wrist sensor. Once again, if you look at these things, very simpler silver-based pattern we have developed over there. And because of this Minder line architecture, it was, and also the separation between these two electrode points. So there is a capacitive element. And that capacitive element, and because of their physical length, it was sensitive to our movement activities over there. So in our lab, we mounted this sensor in a wrist, and then we tried to do different activities like clapping, running, walking, typing, waving, writing, all these different things. And we were trying to capture those signature through our source meter unit. For our laboratory characterization, we are using these units for this current measurement, but in real life, we can also indicate a custom circuit board or electronics which can capture this current signal and then run a smaller footprint machine learning algorithm to characterize those behavior. From our study, we have also done the box plot, like how the signal was being showing the different sort of like activity pattern, what is the median, and also the max mean variation. we also had the confusion matrix-based study so that we can see how well all this activity classification was being done over there. So in our most recent study, we have also started using or forming optical sensors using our printable technology or printing technology. So for our ink selection process, in this case, we have used graphene quantum.ink. Once again, over here, we have used the silver-based interdigitated pattern first. And then on top of these things, we drop casting the graphene quantum.ink. And the property of this, the beauty of this graphene quantum.ink is like it is light sensitive, and the intermolecular spacing creates this tunneling resistance over there. And in addition to that, whenever there is a bending or stress in the substrate level, that defines the particle-to-particle distance and also the corresponding resistance change over there. So we have tested this sample for both electrical and optical characterization. For our electrical characterization, we measure the resistance and with the different bending radius, like we try to deflect the film with 0.5 centimeter, 1 centimeter dia, and then try to see how the resistance is being changed with different deflection portion. We also tested the sample with the spectrometer and how the spectral response was being changed over there. So the same sample over here, it can actually provide both contactless or direct contact-based sensing portion. So this would be a nice addition for our next another level of sensing and characterization one. Some level, this type of sensor could also be used for molecular sensing or liquid sample sensing and so many other parts. So we are actually going for like some other innovative applications of these sensors. So once we have these things, different kind of sensor formation, then also there is also critical need for how can you really create the next level active element, kind of like a transistors, so that we can do much more complex processing and most preferably the machine learning type architecture in our flexible electronics platform. So as you can see, the activation function is the most critical element in any kind of like a machine learning architecture. So definitely this is the most common one, and depending upon the activation function or this nonlinear function, it simply maps our input signal or input features to a higher dimensional space, and then that help us to extract the features, do either regression or classification, that sort of task. So over here, definitely one of the critical need is how to create this sort of nonlinear function, but not mathematical format, but rather on the hardware level. So our target is obviously to create a hardware level architecture, which can do either signal processing or over here, we are targeting the machine learning architecture. So first idea is to create this nonlinear element formation. So in our first investigation, we have used this silver pattern with hexagonal boron nitride in the gap area. And then in the midsection, we have also used graphene P.PSS ink layer. And because of this architecture, our IB profile is simply showing this sort of like a pinch hysteresis. So over here, this is one nice thing that I like to highlight. Unlike traditional like a capacitive architecture where we can see a hysteresis loop, like no touching, but for this sort of architecture, like we're always seeing whenever the signal is crossing through the 0 point or 0 voltage point, always it is touching. And that's what is called the pinched hysteresis. And this is one of the nice phenomena that we observe in our memory strip type devices. So basically what we are forming over here is a inkjet-printed memory store. So unlike like metal oxide based memory store in the silicon fabrication facility, we are forming an inkjet-printed memory store architecture. And this has a huge potential for harder level neural network formation, taking this nonlinear behavior for different level of classification and regression tasks. So this is what we are forming in our lab. But over here, we also try to highlight that this is after having this first level fabrication design cycle. This was a functional init, but then if you also look at the voltage level, it was actually working for a higher voltage, almost to like a 40 volt. The activation voltage was a little bit higher, and that was a kind of like a limiting factor for a low voltage, low power init. So our next focus then goes to how to create a low voltage unit, again nonlinear element, so that we can really integrate these things for our next level harder platform development. So over here, instead of having like a one unit, we have like a multiple pad and also like a kind of like a grid type architecture. And because of these grid type architectures and printing process, including the hexagonal boron nitride overlay and the physical cut, we have seen a very nice feature in the next level. So that's what I'm going to show. But in this phase, I'm simply highlighting, okay, what is the process involved over here? Straightforward one, just like I have mentioned before, like designing the tool, any kind of like a design work softwares. It could be a Photoshop or any PCB design software. And once the design is ready, we can simply send it to the printer for printing our desired substrate. Once the printing is done, the curing process is formed over there. After that, we can do the ink drop casting, drying, and then do some physical cut, and that's it. So with this, so that's why we are actually highlighting that, okay, this is a very, very minimal processing steps involved over here. And even in the room temperature environment, we can easily form this sort of init. But the beauty is that it can give us some nice features, nice behavior, and that can lead us to some sort of like unique platform development. There are some imaging portions that we are actually highlighting, our printing patterns, our cut, and how all the different layers are actually being formed. And now if you look at the IV profile, the voltage current profile, once again, we can see that pinched hysteresis, like whenever the current voltage characteristic is going through the 0 point, always there is like a touching. And that brings that charge trapping phenomena, and which is the core idea behind this memory strip type architecture. We also try to excite our unit from different pad angles. Like so in the previous one, we had like a different pad portion. So how we are exciting or how we are collecting the signals. So depending upon this signal acquisition point or the line, we can also see that like a shift in our characteristics, and that can also bring a another kind of dimension in our signal profile that for our next level mapping, feature extraction, and so many other things. For our characterization, we also we separated the forward path and reverse path and tried to find these nonlinear function. We did a curve fitting tool to form a mathematical expression so that on the first level we can do some software-based learning algorithm. How does this machine nonlinear function is actually behaving in a machine learning architecture? So part of that initiative is simply this curve fitting tool, curve fitting initiative, that how to create or form a mathematical function so that we can investigate this function in a machine learning architecture, how well it behave to do the classification and regression type task. So that whenever we'll take this architecture, printed architecture in a real printed machine learning architecture, how this can provide us some new features. So we tested our nonlinear function in an echo state network or reservoir-based architecture. And over there, we tested it for a time series signal analysis. And as you can see, with other competitive nonlinear function like say ReLU, leaky ReLU, or tan hyperbolic, our proposed function or this printed nonlinear function can also show some appreciable performance over there. So once you have this nonlinear element formation, then our next target goes how to utilize this nonlinear element to create a printable machine learning architecture. And over there, the architecture selection is also a critical one because of this printing process and some cases the low resolution of the printing device. We have to be a little bit careful, like what sort of machine learning architecture could be most suitable over there. So based on our investigation, we have seen a reservoir type machine learning architecture could be the best fitted one. And over there, the principle is, or architecture is simply an input layer where it takes the input signal and then it sends the signal to a reservoir, which is a randomly connected network. And there is no wet training is involved over there. Unlike a traditional neural network where we have to do the weight calculation rigorously. But for this reservoir one, we just need the nonlinear function. And that's the place we saw that our printed nonlinear function or nonlinear element could be the best fitted one. And only trainable layer is the output layer in this architecture. And that training could be a simple pseudo inverse or regression type training layer. And because of that, it is a low data volume, faster training and processing scheme. So to form our printable reservoir architecture, we created this grid. It's like all these nonlinear elements are stacked in row and column format. Right now, we are only showing like a one layer. But based on our need, we can also stack it or in a parallel format. So in that way, we can also increase the number of nodes over here. So once you have this reservoir, it simply mixes our signal with their nonlinear function. Meaning is that whenever we have an input signal to any point of a reservoir, that signal propagates through the network. And during that propagation time, it goes through these nonlinear changes. And that nonlinear changes is basically the higher dimensional mapping of our signal. And then at the final level, from the output lines, we pick either one line or a selective number of lines and do some weight calculation over there. And that's it. That can give us that reservoir-based machine learning architecture. So for our readout layer, we can use a simple layer, or even also we can use a multi-layer architecture over there. So we try to investigate a different kind of learning network on that portion. So which one could be useful? This is like one implementation of like having a 2 layers or portion that how can you really get this sort of classification part. And for our testing portion, we bias the reservoir with a constant current, and then as our input, we use a physical signal, like a physical vibration. So we at the cross points area, we try to create a mechanical drop, and that's how we created a vibration signal, and that vibration signal was actually being propagated through the network. And while it is propagating through the network, it was going through this nonlinear mapping. And finally, from the output layer, we had a mixed signal architecture. So we only selected 4 lines for our output portion. And once we trained a weight level at that portion, we are able to pinpoint like where the input signal was happening. So it's kind of like a localization. So from our output line, we are able to localize how or from where the input signal is coming. So it's kind of like an impact localization, but this could also be used for sometimes for tumorous boundary detection, some other portion like maybe where the infection is happening, something like that. So it depends upon what type of sensing we're actually adding over here. For our first level, we simply use simple mechanical vibration for our first level demonstration, but it can be easily integrated with so many other components too. So our vibration test, we had different signatures over there. We had total 63 time series signals. We also augmented that signal through the wrapper method, and then we're just showing some different signals coming from 3 different areas, how the signatures are being changed a little bit. But once you go through the training process, it was able to classify all the different areas precisely. And here are the results for our accuracy, recall, precision, and some other common machine learning metrics. So finally, we are also going to these like beyond the sensor portions, and then there is also like a critical need for power for our sensing unit. And that sensing, so this power demand is always a critical thing, especially for our sensor unit. Sometimes we can rely on the energy harvesting process, but that power, the energy harvested power, may not be enough for long-term operation. In some cases, we can also rely on the battery, like a nuclear battery, but they are also targeted for extremely low power operation, like kind of like a nanowatt level power operation. So for a decent level sensor power supply and data transfer unit, obviously a most suitable one is called the inductive link. And that's what we're actually investigating in our C2SHIP project over here at Mizu. So as Dr. Skubik has already highlighted, so we are working on the smart pillow project, where the pillow will have sensors, and that sensor signal go to a microcontroller, and then from there to a transmitter, so that the ballistocardiogram signal can be transferred to a mobile app, or all the way to a cloud for next level analysis and data storage. So one of the critical need for that smart pillow is the how can you really do a safe powering to our pillow. And over there, the target was to create a charging mat, which will stay underneath the bed linen, so that it can simply create a magnetic coupling from the lower charging mat to this pillow layer. And so idea is that how to form that sort of reliable charging link, and at the same time form some sort of a mains disconnect, so that the charging can only be done when the pillow is not being used. So that's why the mains disconnect portion was also added over there. So the critical portion that I'm trying to highlight over here, so how to form this sort of like a charging link or the coil formation over here. So on the first level, we are investigating these planar coils fabricated on the standard FR4 type substrate. 2 layers planar coils, and what is their transmission characteristics, and how insertion of a dummy coil can enhance the magnetic field and also improve the power level performance. So this is what actually we are seeing over here. So without any like a meat coil, so we can see a power profile like with this much transmission one, but the moment we are inserting a dummy coil, definitely there is an improvement in the power flow. So this is what we are investigating in our charging scheme. And then we're also bringing these printable Inkjet-Printed coils formation. So over here, we are using the silver nanoparticle ink with our direct ink printing process. And we are investigating a different number of turns, the gap area, inner diameter, outer diameter, these kind of variations, and how it is actually affecting our inductance value, the operating frequency value, and obviously the quality factor. And definitely this coil will give us a nice looking dummy coil pattern, which can actually improve our charging postures. So after covering all of these things, I would like to conclude my session by saying that Inkjet printing is creating a low-cost, affordable design-to-device ready scheme. And definitely, this is targeted for large-scale sensor and device fabrication, much more affordable one. Another benefit is obviously it is providing the biocompatibility with the tissue, substrate, and easy integration with the non-conformal surface level development. And that can create a unique type of healthcare device development. And finally, whenever we are embedding this machine learning architecture with our Inkjet-Printed network, that can definitely facilitate a unique type of edge device, which is our next level IoT device that we are talking about. And it can lead us to our next level or next generation health monitoring applications.
Okay.
So,
Thank you, Dr.
Sure.
Haider.
Thank you.
We are way over time, unfortunately. I know Bijan had a question about manufacturing, I think. Why don't you ask your question, Bijan? Oh, no, we can't hear you.
Oh,
Okay, so
can you hear me now?
yes,
Yeah,
now.
what an amazing tour de force. Is great overview. Thank you. But since we are over time, I would like to go to Dr. Gonabadi that maybe he asked his question. Arash, Dr. Gonabadi, go ahead.
Hello, sorry. Hey, thank you for the presentation. Actually, yeah, I just stated in the chat box. So we are conducting like a study funded by a grant, and we would like to measure like the relative motion between the foot and the insole or the shoe. So because of like different like surfaces or textures, we would like to see how foot or feet are like having relative motion with respect to the shoe or insole. So would you think that your design would be like suitable for like this purpose or not? Thank you.
Yes, no, thank you. Thank you for pointing out this one. Yes, so I think that's the relative motion is definitely one of the part. Like whenever you're talking the shoe sole based sensor unit, so it's mainly about like how this foot placement was actually happening. So definitely, so if you have there is a displacement in our placement or the movement inside our shoe, definitely the capacity profile will be changed, and that change will be captured through our like electrical measurement. So I would say that yes, this is a feasible one, and definitely it could be done over there.
Thank you so much. I appreciate that. Thank you.
Sure.
Yeah, this is very interesting, actually, Dr. Haider. Also, the way that we look at it to some of those shear force or slipping is through measuring thermal stress response, that you find out that actually when you look at the magnitude of the change in temperature as a function of the stress, you may be able to identify also indirectly the amount of the shear force. And I'm guessing that your sensor can capture temperature. So Dr. Skupik, it seems that we pass way over time, as you mentioned. So maybe we can conclude the meeting and I can reach out to Dr. Haider. I see great synergy between works, and Dr. Haider, are really looking forward to collaborate with you and using some of your sensors in our clinical application. My hope is to see a little scalability of those sensors, because personally, I rarely see longitudinal study in clinical study in which they're using those flexible sensors. I don't know whether the issue is with durability, compatibility, or the cost for scalability. So those are some of the items that in another time we can discuss a little further.
And let me just add one other component here too. You know, we've been thinking about these as trying to make a one size fits all, but this technology has the ability to really support personalized sensors. And so maybe we ought to think about how this can be done in such a way that you can actually create a sensor that's custom to the individual that might be more effective.
Exactly. Yes.
Okay. Well, thank you, everybody. Sorry for going over, and we'll hope to see you next week.
Sure.
Yes.
Yeah,
Thank you.
Bye-bye.